Hi, this is your video for section 5.3 on multiplication rule basics. Some key concepts for the multiplication rule are: first, the multiplication rule gives us a way to find the probability of A and B. So this is talking about a compound event linked this time by an and instead of an or. Probability of A and B is the probability that both A and B occur, or that A occurs in a first trial and B occurs in a second trial. In general, to find the probability of A and B, we multiply the probability of event A and the probability of event B. But if the outcome of the first event A affects the probability of the second event B, then we have to adjust the probability of B to account for this. Here's an example of the multiplication rule. Consider a two-question quiz, where the first question is a true-false type and the second is a multiple-choice type with three answer choices, A, B, and C. The correct answers for this quiz are T, true, and B. Find the probability that if you make random guesses for both questions, both answers will be correct. Well, we can use what we already learned about probabilities, and that is, we can figure out what the sample space is. The sample space is all possible combinations of answers for the two questions on the quiz. So this would be true and A, true and B, true and C, or false and A, false and B, false and C. If you're randomly guessing, then the probability of each outcome is equally likely. Since only one of these six includes correct answers for both questions, that is true and B, the probability of guessing that correct answer is 1/6. To use the multiplication rule, we have to recognize this as an and situation. So we are finding the probability that you guess correctly on the first question and guess correctly on the second one. The multiplication rule says that we need to multiply the probabilities of the two separate events to get this answer. The probability of guessing T on question 1 equals 1/2, while the probability of guessing B on question 2 equals 1/3, since there were three answer choices. So the probability of T and B would be 1/2 times 1/3, which equals 1/6. Notice how we got the same answer using the multiplication rule as we did by looking at the sample space and assuming that each of those outcomes in the sample space was equally likely. Now let's talk about independent events. Two events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. If A and B are not independent, then they're said to be dependent. Here's an example of independent events. Suppose that you draw a card from a standard 52 deck of cards and then roll a die. Are the events draw a heart and roll an even number dependent or independent? Well, the results of choosing a card do not affect the results of the die toss, so these two events would be independent. Now, suppose that you draw a card from the deck and then, without replacing the card, draw a second card. Are the events draw an ace on the first draw and draw an ace on the second draw dependent or independent? Well, if the first card drawn were an ace, then there would only be 3 aces left in the deck. If the first card were not an ace, then there would be 4 aces left in the deck, but only 51 cards. This means that the results of the first event do affect the probability of the second event. So the two events are not independent, they are dependent. In other words, what happens in the first event has an effect on the probabilities for the second event. For the multiplication rule, we can look at this in two different ways. The first one is the intuitive way to look at it. So the intuitive multiplication rule says, to find the probability of A and B, the probability that event A occurs in one trial and event B occurs in the next trial, multiply the probability of event A by the probability of event B. But be sure that the probability of event B takes into account the previous occurrence of event A. Now, the formal multiplication rule actually talks about multiplying together probabilities. So this says that the probability of A and B equals the probability of A times the probability of B. Here's an example of using the multiplication rule. Again, suppose you draw a card from a standard 52 deck of cards and then roll a die. What is the probability that you draw an ace and roll a number greater than 4? One of the important things to notice in this problem is that we have two events that are connected with an and. So we're looking for the probability of drawing an ace and rolling a number greater than 4. And tells us that we should be thinking about using the multiplication rule. Now, we already determined that these two events are independent, so we can find the probability of each event separately and multiply the results together, without worrying about the probability of one event affecting the probability of another event. The probability of drawing an ace is 4 over 52, or 1 over 13, since there are 4 aces in a standard deck. And the probability of rolling a number greater than 4 is 2/6, or 1/3. So the probability of drawing an ace and rolling a number greater than 4 is those two probabilities multiplied together. So this would be 1/13 times 1/3, which gives us 1/39. If we put this in decimal form, rounded to 4 decimal places, it would be 0.0256. Now, suppose you draw a card from the deck, and then, without replacing the card, draw a second card. What is the probability that both of the cards drawn are aces? Now, these two events are not independent since the card is not replaced after the first draw. What that means is that for the second event, we have to take into account what happened in the first event. So the probability of the first card being an ace is 4 over 52, or 1 over 13. But for the second draw, we're assuming that the first card drawn was an ace. So for the second draw, there are only 3 aces remaining in the deck, which now only has 51 cards. So the probability of the second card being an ace is 3 over 51, or 1 over 17. Now we can use the multiplication rule, so the probability of both cards being aces is 1 over 13 times 1 over 17, which gives us 1 over 221, or 0.0045. One thing to notice in this problem is that it doesn't specifically say and. You have to read that from the problem because it's talking about the fact that both cards drawn are aces. So that means the first card is an ace and the second card is an ace. So you have to think about it and put the and in there for yourself. Here's another example. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there's a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So let's let event A equal the equipment is defective, and let event B equal customer uses the equipment within 1 year. In order for a customer to make a valid warranty claim, both of the events here have to occur. So it would be event A and event B. Now we can assume that these two events are independent. And again, for a customer to make a valid warranty claim, both events have to occur. The proportion of customers that do this is the same as the probability of both events A and B occurring. So to get the probability of A and B, we use the multiplication rule. So we have 0.10, which is the same as 10%. That's our probability of event A. And 0.30, which is the same as 30%. That's our probability of event B. We multiply those two together and get 0.03. Now we have the multiplication rule for multiple events if we have more than 2 events. So if E1, E2, E3, and so on up to En are n events, then the probability of E1 and E2 and E3 and all the rest of them up to En is just equal to the probabilities of each one multiplied together. And of course this is automatically true if all these events are independent. If they're not independent, then you have to take into account how the probability of one affects the probability of the next one. Here's an example. Suppose you draw a card from a standard 52 card deck of cards, record the suit, and then replace the card. If this procedure is repeated 4 times, or in other words, with 4 trials, what is the probability of drawing 4 hearts? Well, each draw of a card, or each trial of the procedure, is an independent event because the card is replaced after each draw. The probability of drawing a heart on any one draw is 13 over 52, or 0.25. The probability of drawing a heart 4 times in 4 trials is the same as the probability of heart and heart and heart and heart. So this is the first draw, the second draw, the third draw, and the fourth draw. Our multiplication rule tells us that this is the same as each of these probabilities multiplied together. And since they're all independent, then the probability is 0.25 for each one. So if we multiply 0.25 times itself 4 times, we end up with 0.0039. Here's one more example of using the multiplication rule. Suppose you draw a card from a standard 52 card deck of cards and record the suit. If this procedure is repeated 4 times without the cards being replaced, what is the probability of drawing 4 hearts? So the only difference between this problem and the last example is that this time the card is not replaced. So in this case we're drawing without replacement. That means that the events are not independent, and we have to take into account how each draw affects the remaining draws. So the probability of the first card being a heart is still 13 over 52, or 1/4. The probability of the second card also being a heart is 12 over 51, because if our first card was a heart, we only have 12 hearts left in the deck, and we only have 51 cards left in the deck. The probability of the third card also being a heart is now down to 11 over 50. So each time we're reducing the number of hearts in the deck, and we're also reducing the number of cards in the deck by 1. The probability of the fourth card also being a heart is 10 over 49. So we started out with 13 over 52, then went down to 12 over 51, then down to 11 over 50, and finally down to 10 over 49. So again, the probability of heart and heart and heart and heart is the same as the 4 probabilities multiplied together. That would be 1/4 times 4 over 17 times 11 over 50 times 10 over 49. And that comes out to be 0.0026.